This question challenges you to test your understanding of the OAS method within the Ledwall-Wolff estimator. It asks you to identify correct statements about OAS, which is a specific algorithm for calculating optimal shrinkage intensity in the Ledwall-Wolff covariance estimation technique. I have discovered that statement A is false. While OAS aims to improve the covariance matrix, it doesn't guarantee a positive semi-definite result. The sample covariance matrix itself might not be positive semi-definite, especially with many dimensions and limited samples, and therefore statement A is incorrect. Statement B is true. OAS involves optimizing a scalar value, the shrinkage intensity, a process generally computationally intensive than using a pre-computed value, as in the shrinkage method. That's right. Statement C is true. Ledwall-Wolff is a shrinkage estimator, and OAS is its algorithm for finding the optimal balance between sample covariance and the target matrix, usually a scaled identity matrix. Absolutely. Statement D is also true. The accuracy of any estimation method, including OAS, depends on factors like the amount of data, sample size, and the complexity of the data, dimensionality. I'm using the Ledwall-Wolff method, specifically the OAS, Ordinary Approximation Scheme, method, from the Sklearn library in Python to estimate a covariance matrix. The Ledwall-Wolff estimator is a fancy way of improving the regular sample covariance matrix, especially when dealing with lots of variables and limited data. First, I need my data. This is a collection of numbers representing measurements or observations of multiple variables. The data is the heart of the covariance matrix calculation because it feeds into the initial sample covariance matrix estimation. Before using the OAS method, I calculate the traditional sample covariance matrix. This matrix shows how much the variables change together, how strongly they are related. Finally, after applying the OAS method's shrinkage calculation, I obtain a refined covariance matrix. This matrix is an improved estimate over the simple sample covariance matrix and often performs better in high-dimensional situations or when sample size is limited. The OAS method helps to achieve this improved estimate by optimally combining the sample covariance matrix with a target matrix, usually a scaled identity matrix. This question asks you to identify the correct statements about the ordinary approximation scheme, OAS, used within the Ledwall-Wolff covariance estimator in the Sklearn library. I'll guide you through each option to find the correct answers. Think of it like this: if I have a tiny sample of data points, or if my data has many variables, it's harder to accurately estimate how those variables relate to each other. The OAS method, like any statistical estimation technique, struggles with these limitations. So, more data points and fewer variables usually lead to a better estimate of the covariance. This is a key characteristic of covariance estimation methods. The Ledwall-Wolff estimator is a shrinkage estimator. Imagine you have a slightly inaccurate initial estimate of something, the sample covariance matrix. Shrinkage methods improve it by blending the initial estimate with a more stable, but potentially less accurate, target matrix, often a simplified version like a scaled identity matrix. OAS is one specific way the Ledwall-Wolff estimator does this calculation to get the best balance. The shrinkage method in Ledwall-Wolff uses a pre-calculated shrinkage intensity. The OAS method, however, must calculate this intensity, which requires more computation. It's like the difference between using a pre-made recipe and figuring out the recipe ingredients from scratch. OAS involves optimization, making it slower. A positive semi-definite matrix is like a well-behaved matrix that guarantees sensible results. While OAS* aims for a better covariance matrix, I can't guarantee it always produces a perfectly positive semi-definite one. Numerical issues or limitations in the data itself might prevent it. Let's dive into the Ledwall-Wolff covariance estimation technique, specifically focusing on the ordinary approximation scheme, OAS, method. I'll explain what it does and why we might choose it. The Ledwall-Wolff method is a clever way to improve on the simple sample covariance matrix, especially when you're dealing with a lot of variables and not that much data. OAS is one of the ways it figures out the best way to do that. This is a multiple-choice question about the ordinary approximation scheme, OAS, method within the Ledwall-Wolff covariance estimator. We're going to evaluate several statements about OAS to determine if they are true or false. This statement is false. While OAS aims for a better behaved covariance matrix, it doesn't guarantee positive semi-definiteness. Remember, a positive semi-definite matrix is essential because it ensures the covariance matrix is well behaved. However, there are cases where it can fail to produce one, particularly with limited data or many variables. So, we need to remember that it's a goal of OAS, but not a guaranteed result. I'll explain this one. The statement is true. The OAS method involves finding the optimal shrinkage intensity through an optimization process. It needs to solve an equation to find the optimal adjustment to the covariance matrix. In contrast, the SHRINKAGE method uses a simpler, pre-calculated formula, therefore, making OAS computationally more demanding. This statement is absolutely true. The Ledwall-Wolff estimator is a shrinkage method, which means it combines a simple sample covariance matrix with a target matrix, often a scaled identity matrix, to create a better estimate, especially in higher dimensions. The OAS method is a part of this process. It just calculates how much to shrink. This is true. The accuracy of any covariance estimation method, including OAS, is directly influenced by the amount of data you have, sample size, and the number of variables you're tracking, dimensionality. More data usually leads to better estimations and fewer variables help as well. This quiz tests your understanding of the Ledwall-Wolff covariance estimator, specifically its ordinary approximation scheme, OAS, method, used in Sklearn. We'll examine several statements about OAS and determine which are true. Get ready. I find that the OAS method is indeed more computationally expensive. It involves an optimization step to find the optimal shrinkage intensity, unlike the simpler formula used by the shrinkage method. Think of it like this. The shrinkage method uses a pre-calculated shortcut, whereas the OAS method calculates the best path. That's correct. The Ledwall-Wolff estimator is a SHRINKAGE estimator, and OAS is one way to do it. It blends the sample covariance matrix, your initial estimate, with a target matrix, often a scaled identity matrix, to get a better, more stable result. It's like taking a weighted average to smooth out the noisy bits. Absolutely. Like any statistical method, the accuracy of the OAS method is affected by how much data you have and the number of variables. More data and fewer variables usually lead to a better estimate. It's like having more puzzle pieces makes the puzzle easier to solve. This one is false. Although OAS aims for a well-behaved covariance matrix, it doesn't guarantee positive semi-definiteness. Numerical issues can pop up, especially with high-dimensional data, resulting in a matrix that's not quite positive semi-definite. Think of it as aiming for perfection, but sometimes you may slightly miss the mark. This refers to a specific method, OAS, ordinary approximation scheme, used within the Ledwall-Wolff algorithm to estimate a covariance matrix. The Ledwall-Wolff estimator is a popular technique in statistics and machine learning for improving the sample covariance matrix, especially when dealing with high-dimensional data or situations with limited samples. The OAS method is a key part of how the algorithm calculates the optimal shrinkage intensity. This is a multiple-choice question testing my understanding of the OAS method's properties and behavior within the context of the Ledwall-Wolff covariance estimation algorithm. I think the OAS method is computationally more expensive because it involves an optimization process to find the best shrinkage intensity. The shrinkage method, on the other hand, uses a pre-computed value, making it faster. The OAS method is a part of the Ledwall-Wolff estimator, which is a shrinkage estimator. A shrinkage estimator combines the sample covariance matrix, calculated directly from data, with a target matrix, often a scaled identity matrix. This blending reduces the impact of noise and improves the overall estimation of the covariance matrix. The OAS method determines how much of each is combined, in effect finding the optimal balance. I understand the accuracy of any statistical method like the OAS method is affected by the size of the data sample and how many variables are being measured, dimensionality. More data points generally lead to better estimations because there is less uncertainty. Also, having fewer variables reduces the complexity, therefore leading to better accuracy. While the OAS method aims for a better conditioned matrix, it does not guarantee a positive semi-definite covariance matrix. A positive semi-definite matrix is one whose eigenvalues are all non-negative. Numerical issues or the nature of the data itself can sometimes lead to violations of this property, especially in high-dimensional datasets with limited samples. Therefore, this statement is false. This question tests my understanding of the OAS, ordinary approximation scheme, method within the LEDOITWOLF covariance estimator in the SCIKITLEARN library. I need to identify which statements correctly describe OAS's properties. Let's dive in. I find that the OAS method is indeed more computationally expensive than the SHRINKAGE method because OAS involves an optimization process to find the best shrinkage intensity. The SHRINKAGE method uses a simpler, pre-computed formula, making it faster. I observe that the LEDOITWOLF estimator, and consequently the OAS method within it, is a shrinkage estimator. This means it cleverly combines the sample covariance matrix with a target matrix, often a scaled identity matrix, to produce a more robust and reliable estimate, especially when dealing with high-dimensional data. I notice that the accuracy of any covariance estimation technique, including OAS, is impacted by the amount of data I have, sample size, and the number of variables, dimensionality. More data and fewer variables generally lead to better estimates. It's a bit like trying to understand a complex system. The more data and simpler the system, the easier it is to understand. I discover that the OAS method doesn't guarantee a positive semi-definite covariance matrix. While it aims to improve the condition of the covariance matrix, numerical issues or the nature of the data itself can sometimes result in a matrix that's not quite positive semi-definite.